Hey guys, it's Simon and welcome back to the LibGDX Kotlin RPG tutorial series. So in the last part we learned, or we introduced now, a movement of our entities, actually of our player. So what we are now able to do is that inside our game, when we press up, down, left, right, we can move our player around. There's a collision already happening with our other entities, so we can currently move them around. Which we might fix in this part. Let's see how long it gets. And what we are now going to solve is that we will have a rendering issue if our physics world is not updated the way we are currently updating it. So at the moment it looks very good. We don't have any stuttering, but you could have that actually when your game does not run at a good frame rate, or for example, for whatever reason, you need to reduce the amount of updates because it's too time consuming to do the physics simulation 60 times per second, then maybe you need to go down. And currently we would have there a problem. So if we would go down, you see now our player movement is not very smooth. He's stuttering around, and we are going to solve that. And this is part of our fixed time step approach that we introduced 2 parts ago. The part which is currently missing is the interpolation. And how does that work? So it's, would say, quite simple. What we need to do now is simply we need to store the position of an entity before we call the step method, so before the entity gets updated. And afterwards we have then of course the real position, so after the entity got updated with the movement. And now between the previous position and the current position, we simply want to interpolate between those 2 positions to get a smooth experience again for the player. And how is that working? So luckily for us, because I am the developer of Flex and I had this problem with Ashley with the LibGDX entity component system, Flex has that built in. So what we need is, when we would check out our onTick method, the update method, so the onUpdate method. So there currently we are using this onTick, which is also calling then the onTick of the entity, which gets called with a fixed rate. But in addition, you see that here below there's also a so-called onAlpha method. And this is actually called then again per frame. And the value, so this alpha value, is a value between 0 and 1. And it defines how close are we to the next full frame. So with this fixed time step approach, there's always a little bit of a delta time. Either it's not enough to go to the next frame, or it's would be too much. So if we go, for example, if we tick multiple times per frame, then there is some leftover, maybe also for the next frame again. And this value is, as mentioned, between 0 and 1 and defines like the percentage until we reach the next frame. A value of 1 would mean that we have exactly the step rate, and we would go here into onTick. And any value below 1 is then a leftover of a frame. And this information, so this alpha value, is usually then growing. So when we are stepping and we would exactly have a frame rate according to our fixed time step approach, then the alpha value would always be 0 because it's perfectly aligned. But if it's slightly different, then this alpha value fluctuates between 0 and 1, and we will use it for the interpolation. So usually this alpha is growing slowly from 0 to 1 until it reaches then the next frame, and then again it goes back to 0 and fills up to 1. So have a look at that and think it a little bit through, because that is something important for what we are going to implement now. So what we need, as mentioned, we need to remember somehow the previous position of our entity before we are updating the physics world. So we are simply storing that in the physics component. So there we store the previous position, which is again a vector 2. Then when we go back to our physics system, so what we are going to do now is that in our onTick entity, so this is when before our word gets stepped actually. So onTick is calling this onTick entity, and then we update the word. And before we update the word, we want to remember the position of our entity. So let's do that up here. So in our physics component, we have the previous position, and this is actually simply from our body the current position. So before it gets updated, we store this position. And now for the rendering, we remove that part here, and we actually move that in this on alpha method, because there we are doing now the interpolation. So let's move that down. So what we need is again the physics component and also the image component. And the image component is actually not needed at the top anymore, so we can remove that. And here it's not on alpha, that was my mistake. It's actually the on alpha of an entity. So let's remove on alpha. We want the default behavior that it calls on alpha entity of all the entities of that system. And now we're going to do something. So instead of setting the position of the image to the body position, which is now the updated body position, so this is the position after we called word step in that scenario. Now we want to have an interpolation. So we have the body x, and we also have the previous x and the previous y, which is from our physics component, the previous position. And now the set position is simply an interpolation between those, between the x and the y value of those two positions. So in LibGDX, in the math utils library, there is a function which is called lerb, which is a, I think, how is it called? A linear interpolation, I think it's called. And from which value do we want to interpolate? So it's the previous x, and we want to go to the real position of the body, and the progress is a value between 0 and 1. 1 meaning that it will return the x, this position, so the to value, and 0 would mean it returns the from value. And that perfectly plays together with what we have here in this alpha approach. So we simply pass in here the alpha value. And the same for the y coordinate. So here we also pass in the y, the previous y position, and the new y position, and also interpolate there. And that should already be it. So let's try that out. So let's first of all return it back to this 10 frames per second. And now you see, so the physics body is still stuttering because it only gets updated so 10 times per second. But let me make that bigger, that it's easier for you to see. But the graphic itself is moving very smoothly. So the player itself, if he would not see this box to debox, which he doesn't, this is just some debug information, the player itself only sees some very smooth movement. And this is what we want to have. And this is what this interpolation approach is fixing for us. Perfect, but yeah, for us, we return it back to the 60 frames per second because this is really the target value that we want to have. And still also with that value, you will see that. So now the box2D body is not stuttering that much. From time to time, it might do that, but the graphic or the rendering representation is still very, very smooth. So this is perfect for any game that we want to have. Okay, and what is also maybe a little bit tricky, and you might mess that up a little bit, is when it comes then to the camera locking. So what I mean with that, this is also just a small system that we implement in this part, because I see it's rather short, so we can add that in. Currently our player moves around and the camera always stays static, so it does not move with the player. And what we want to do now is that we focus the camera always on the player, so that the player is always in the center of our camera. And currently we don't do that. So let's introduce there a new system. So let's call that player system. Sorry, not the player system. Let's call that a camera system, of course. So what is that camera system doing? It's iterating over all entities which have a player component and which also have an image component. I come to that in a moment. There would be a problem if we would have multiple player entities, which in our case we don't. We always just have one. But if we would have multiple ones, then of course with the approach that I chose here, the camera would always focus on the last entity of that family. So maybe if you have more entities, or if you want to have a dynamic or a more flexible approach that you focus the camera on just specific entities, then maybe introduce like a camera lock component, for example, and add this component always just to one specific entity in your scene, and then the camera will be locked to that specific entity. For me, because it was easy, I just took the player component in that case, because I only have one player, so I can lock the camera to that specific entity. Okay, so what do we need? We need our image components. And we need a camera, which we get from our stage. So here we store our camera, which is from our stage, the camera. Okay, and this system is an iterating system again. And what are we now going to do? So what we want to do is that we center the camera on our player. So on our entity that we get in here. So we get from our image components the image itself, so the position, and set then the camera position. So the camera has a position, and that one we set to the image x coordinates, the image y coordinates, and we keep the camera set value to whatever value that is. Now let's add this system to our worlds. Let's do that before we render, so that the important part is that it's happening before the rendering, because we update the camera position and therefore also the view, so that the part which gets shown to the player, and then in the render system we use the camera. So that's why we do the update before we are rendering. And let's see, so that should now already lock the camera to the player. And it does that. So now, as you see, when we move around, the player is now always centered in our view. What is not so nice is that currently we can look outside of the map and then simply see the black background, which we don't want to have. We're gonna fix that also with a small tweak. What is important is that we really use here the image component for the camera locking and not the physics component. Why don't we use the physics component? Let's quickly change the code a little bit, that you can see that as well. So rather quickly, it's just a quick and dirt implementation. We get here also the physics components. And now let's not use the image components, we use the physics component, and there the body position X and the body position Y. Let's ignore here the fact that we would need to reduce half of the width and the height again of the image. So for now, we just take the center of the body. Let's run our game. So it looks like it is doing the same, but I'm not sure if you can see that in the video, but the graphic itself is, I don't know how to describe that. It's stuttering a little bit, so it does not look very sharp. It looks like I'm a little bit drunk and maybe drink already 5 or 6 beers. So it's a little bit strange. And why is that? The reason is that with our interpolation approach, the body position only gets updated currently with the 60 times per second. Could be worse if we again reduce the physics system to maybe even just 10 times per second or things like that. And that means if we update it to the physics body position, then the camera position also only gets updated with that fixed rate. But in between, so when we move the camera, then slowly the player is then getting interpolated to actually the center of the camera. And because of that, we have this strange rendering behavior that we just saw, because the rendering position of our player and the camera position are not aligned with our interpolation approach. So that's why we must not use here the physics component. We really need to use the image here to have the correct rendering behavior and also camera locking mechanism in place. Okay, quickly let's fix the problem that we can move our camera outside of the map. So that is fixed rather easily. So what we need to do, we need to make our camera system an event listener. Then we need to react on these events. And on what kind of event are we reacting? Of course, we check if our event is a map change event. That is the important part for us. And there we want to get out the size of our map. So that's one we are going to store that. So let's also move up here. So there we store the maximum width and the maximum height of our camera boundaries. And the maximum width is simply from our map, the width to float, and the maximum height is also from our map, the height to float. Just that you are aware of that. So the map has a tile width, which is in our case it would be 16 because we have 16 by 16 tiles. Then it has a width, which is the amount of tiles on the x coordinate. And it has a total width, which would be the width times the tile width. So this is really the total amount of pixels. In our case, we are really only interested in the width of the map, and the same for the height on the y coordinate, or y-axis, not y coordinate. Okay, and with that, what can we now do? We can now define the view width, which is from our camera, the viewport width. So what does our camera see? So what is the width of the viewport of the camera? And there we only want to have half of it, and the same for the height. And why do we need those values? Because the position where we are setting now our camera, which is the image position here, but that one we want to limit, so it has to be between two values. So it's either simply the view width, which means that the smallest amount is half of the viewport width of our camera, which means that we can only go to the left part of our map. I try to draw that then later on in a graphic that it's easier to understand. And the maximum value is the maximum width of our map, and here it is minus half width of the viewport, so that we can only go at most to the right edge of our map. And the same we do for the y coordinate, but here we do the view height, the max height, and again the view height. And with that little piece of magic, we should now be bound with the camera inside of our map. So when we go to the left, you see it does not go outside of the map. Same for the bottom here. And when we go to the right and up direction, then at some point it will also stop. So there you see it. So we have our boundaries of the camera are exactly the size of our map. And why does that work? So let's take that graphic here. So imagine here this main camera boundary, that would be our map. And then we have our camera with a specific viewport. So initially we are at the location 0, 0. So our camera is here at the corner. And actually its position is, I think, always the center of the viewport. So similar to box 2D, it's inside of this rectangle. Yeah, sorry, with that, I'm not 100% sure if that is correct. I think the position is really 0, 0 in that case. But the width of the camera would be that one here, and the height would be that one. And when we say in our system that our camera cannot go to the 0 location, it can only go to half of its width on the x-axis. So that's why we exactly stop here on the left corner, because if we always move it half of its entire width to the right, so that is the minimum here, so then it can really only move up and down on the left edge of the map. So this is why that one is working. So this is why we use this half of the viewport width and half of the viewport height to limit it to the different edges of our map. So that's the math behind that piece of code. And yeah, so that would be it, I would say. So we actually covered two things in that part. So we had this interpolation, which fixed the rendering for us, and we have a very smooth render experience when we move and update our physics world. And we also introduced our camera system so that we can actually move through the map as well, which is great. Good, so there's one small piece now missing that I will cover in the next part, which is the box 2D contact listener, because right now when we collide with a slime, then we move its body around, which is not that great. And also our bodies are way too big, so we don't want them to be that big. So that is what we are going to solve in the next part. Thanks for watching and have a nice day. Bye bye.